Hello, my name is Leah O'Connor, presenting to you the Tokamak Fusion Test Reactor. The Tokamak Fusion Test Reactor, also known as TFTR, developed by the Princeton Plasma Physics Laboratory in the United States, aimed to explore the potential of magnetic confinement fusion for energy generation. Inspired by earlier tokamak prototypes and the groundbreaking work of Soviet physicists Andrei Sakharov and Igor Tamm, the TFTR was a feat of engineering, towering 60 feet high and weighing over 3,000 tons. Constructed over 10 years, it became operational in December 1982. Housed at the Princeton Plasma Physics Laboratory in New Jersey, TFTR operated until 1997, making significant contributions to plasma physics and fusion research. With its donut-shaped vacuum, magnetic coils, neutral beam injectors, radio frequency heating system, and cooling system, TFTR demonstrated the ability to withstand extreme heat, confine plasma, generate fusion energy, and advance nuclear fusion research. This impressive device furthered our quest for sustainable and clean fusion energy solutions. Now let me take you through how this particle accelerator works. Our story begins inside a vacuum chamber. Here, scientists inject a fuel mixture of hydrogen isotopes, deuterium and tritium, into the heart of the reactor. Powerful heating systems kick into action, raising the temperatures 100 to 200 degrees Celsius. Surrounding the plasma, we find a complex arrangement of magnetic coils. The magnetic field forms a mesmerizing dance of toroidal and poloidal lines. Ensuing, the plasma stays confined and stable within the reactor. And there, amid the magic embrace, the magic of fusion occurs. The hydrogen isotopes within the plasma collide and fuse together, releasing a torrent of energy. A beautiful transformation takes place as deuterium and tritium nuclei merge to form helium and emit high-energy neutrons. The fusion reaction generates an abundance of high-energy neutrons. These energetic particles interact with a special blanket of lithium surrounding the plasma chamber. This interaction transfers energy to the blanket, heating it up significantly. The heat produced in the blanket is transferred to a coolant, like a flowing river of energy. The coolant carries this precious heat to a working fluid like water, which transforms it into steam, then energy. Now let's explore how this relates to you. Let's begin with the core of grade 12 physics, electricity laws. TFTR harnesses electromagnetism through its powerful magnetic coils. These magnetic fields, shaped by Ampere's law, play a crucial role. The very heart of TFTR lies in energy conservation, the law that energy can neither be created nor destroyed, only transformed, learned this year. Within the scorching hot plasma, nuclear fusion reactions convert mass into immense energy, a principle beautifully demonstrated. Throughout this course, we learned a lot about magnetic fields, forces, and electromagnets. TFTR harnesses the power of magnetic fields to stabilize, confine, and heat the plasma, a state of matter where energy is transferred between different states like thermal and kinetic energy. It's awe-inspiring how plasma undergoes nuclear fusion without creating or destroying mass. Now, let's explore the invaluable data and discoveries achieved at TFTR. In 1997, it reached an astonishing milestone, achieving the highest fusion output, 10.7 megawatts. But that's not all. TFTR revealed the secrets of waves through plasma using neutral beam injections and radio frequency heating.
Now we're going to be looking at the benefits and drawbacks. Here we will be doing an evaluation of the advantages and disadvantages of the tokamak fusion reactor. The tokamak fusion reactor offers numerous benefits, including inherent safety. The fusion reactor stops if conditions deviate from precise requirements, preventing the kinds of meltdown associated with fission reactors. The fuel for fusion, hydrogen isotopes, is abundant in seawater, providing a virtually limitless energy source. Additionally, fusion reactors emit minimal pollutants and produce less long-lived radioactive waste compared to traditional fission reactors. However, there are still associated drawbacks. The technological hurdles remain. We currently struggle to sustain fusion reactors for long durations, impeding continuous power generation. The financial demand is also high, with substantial investment requirements to build and operate fusion reactors. Finally, achieving a positive energy balance is a challenge. More energy is needed to start the fusion process than it currently yields. Now we're going to be looking at the section 4 of our assignment, which is STSE connections. Here, we're going to be unpacking the global, environmental, economic, societal, and technological implications. So first, we're going to be starting with environmental. The environmental benefits of the tokamak fusion reactor are significant. It provides a cleaner energy source, emitting minimal pollutants and reducing our carbon footprint. Unlike fission reactors, fusion creates less long-lived radioactive waste, addressing a key environmental concern. Tokamak reactors utilize isotopes of hydrogen, which are abundant in seawater, offering a virtually limitless fuel source. The fusion process also has safety features that minimize the risk of catastrophic meltdowns. A remarkable example is China's experimental advanced superconducting tokamak, which is known as EAST. This tokamak reactor has achieved significant milestones, including sustained periods of plasma confinement and temperatures, exceeding those in the core of the sun. This demonstrates how fusion power can satisfy global energy demands while mitigating environmental impacts. Next, let's look at the technological implications. The tokamak fusion reactor has revolutionized power generations with its controllable fusion method, paving the way for innovations beyond energy. Developed for plasma containment, its superconducting magnets now serve various fields, including medicine and transportation. It symbolizes efficient energy production, harnessing nuclear fusion's immense power. A key example of the impact of this technology is the International Thermonuclear Experimental Reactor, which is known as the ITER project. ITER is a global initiative aiming to make fusion a practical and reliable energy source. It showcases what we can achieve when nationals collaborate on a scientific mission. More than its present contributions, the tokamak reactor is a fueling future scientific and technological breakthrough. Its wide adoption could fundamentally transform our global energy infrastructure, reshaping how we generate and use power today.
Social implications, sustainability, energy source, fusion reaction might eventually replace fossil fuels, lowering greenhouse gas and emission and slowing climate change if they are successfully constructed. Energy security, fusion energy could decrease the dependence of nature and external energy source and increase energy security by reducing the world's dependence on limited fossil fuel stocks. Economic growth and job creation, fusion reactor development and construction would involve a substantial energy and skilled labor, perhaps resulting in economic growth and creating jobs in the scientific, engineering and construction in industries. Energy accessibility, fusion power had the ability to bring independent electricity to isolate or underdeveloped areas that do not currently have access to. This could result in better living circumstances and better chances of social and economical advancement. Economical implication. High initial investments needs a substantial initial cost to build and run due to the complicated and cutting-edge nature of the technology as well as the requirements of lengthy research and development. The building cost might be high. Energy marketing disruption. Tokamak fusion has the potential to upend currently energy markets if it provides to be a widely used and financially viable energy source. Energy dependent section and conventional energy business such as coal, oil, and gas may be affected in many ways economically by this. To account for this changing energy landscape, government and business may need to modify their policies and investments. Job creation and economic growth. Energy manufacturing, research, and maintaining are just a few industries that might see job growth due to the development, building, and operating of Tokamak fusion reactor. The flood of skill work possibility may add the expansion of the local and national economies. Economic sales. There are chances that economies of scale will begin to operate when additional tokamak fusion reactors are created and run. Over time, cost saving and more effective building techniques can result from the mass manufacture and a standardization of reactor component.